My name is Eric Johnson. I am an employee of Aruba Networks. I manage their outdoor product line. This content is a very small subsection of about 8 hours of training that I do for Aruba sales engineers and customers. So I'm very pleased to have the opportunity to present today. I really appreciate you guys taking the time. I feel the mic doesn't, there's no speakers in here. The mic is for the recording. So I am completely a fish out of water in here, guys. I am a physical layer engineer. So the talks you guys are getting on the SDR and other things like that. But we're going to talk about antennas today. We're going to talk about 11AC. We're going to talk about where some of these magic numbers come from, like 1.3 gigabits per second. So we're going to do a bit of a deep dive down the technology well. If you guys have questions, I prefer to answer them as we go along. So please feel free to jump in, and we'll keep the thing interactive. Okay, so we're going to talk a little bit about the physical layer, and then we're going to dive into the data rates. I'm going to show you where those numbers come from, so you understand how we get to them. We're going to spend some time talking about antenna basics and understanding how antennas actually work in your environment, because my experience in this industry is that there's a lot of misinformation, a lot of misunderstanding. Then we're going to talk about 11AC beamforming. It is absolutely not what you think it is. It works a little bit different than the way most people perceive it. And then we're going to talk briefly about some field test results. And so here we go. All right, so just to give you guys a quick primer, I know that most of you know this. 11AC is really an evolutionary standard. 11N changed the game big time. The introduction of MIMO, multi-in, multi-out antenna technology and radio technology was really groundbreaking. It completely changed the way that we thought about doing commercial radio solutions. 11N, of course, was supported on 2.4 and 5 gig. It brought 40 megahertz channels, which was an extension. There was actually some physical layer stuff that had to happen. Some of the old radio technologies that were used, the 11A and B, stopped working because of the fact that we had multiple channel bandwidths. We introduced 64 Qualm. I'm going to talk about what Qualm is today as I go through this. There was beamforming in the standard, but the standards body actually made a huge mistake. Anytime you put something into a standard that's optional and you give more than one way to do it, that's a guarantee that it'll never be implemented. The difference in 11AC is that there's only one way to do 11AC beamforming. That is now the de facto way of doing it, and the industry is seeing wide adoption. Broadcom has implemented that across the board. Atheros is going to be doing that on their Wave 2 chipsets. All right, and then, of course, with all of this stuff, it's backwards compatible with the previous standards. 80 megahertz channels. Now, this is a really interesting statement. Why is it 4.5 times faster than 20 megahertz? Isn't it just 4 times as wide? I'm going to show you why that's the case. The 80 megahertz channel has to be contiguous. This is not like the old days when you talked about what they called turbo mode, where they'd run 2 channels and you'd try to bind them together and it would create all kinds of spectral crap in the middle. This is a clean implementation of an 80 megahertz wide channel. It's actually, this is something I'm not going to touch on today, but this is actually a really neat feature that gives you the backwards compatibility. And it actually allows 2 radios that are sharing the same 80 megahertz channel to be split. They can transmit at the same time on 40 or 20 megahertz here and 20 megahertz there. It can be extended to 160 megahertz. On the commercial side of things, we don't see that that's necessarily going to be useful. There just isn't enough spectrum. All right, so now we're going to take a little bit of a dive here. Lots and lots of terms, so please try to keep up. And if I confuse anybody, we can back up and go over it again. But this is what you're looking at when you're talking about 802.11n, 802.11g, 802.11ac. This is ofdm modulation, orthogonal frequency division multiplexing. What that means is the information is actually divided up on a whole bunch of individual frequency tones. Okay, so if you think about this normally, you would have a single carrier, all your data would be encoded on it, it would be sent over the air. That's the way 802.11b works. You'd receive it, decode that single stream. This is a whole bunch of data sent in parallel. Each of those tones is carrying 1, 2, 4, 6, or now 8 bits of information. And so depending on how many tones you have or how many carriers, that determines how much data you're pushing over the air at any given time. So if we go back to 802.11a and G, we had 52. So these things are always based on factors of 2. So the base setup was 64. You have to turn off some tones on each end to create space and frequency. Those are called guard tones. So they have an amplitude of 0. And then there's a couple of other tones in the middle, which are called pilot tones. They contain known information. There's no actual useful transmission of data on that. So those are called pilots. And the pilots are actually used to help the receiver decode the channel and receive the bits. Okay. The pilots are coded, and they're coded in a very particular way to help the receiver to receive them and actually extract phase and amplitude information about the channel. That's right. And it's actually, the pilot definitions are actually defined in the standard as well. Okay? So with the original 11A and G, out of those 64 tones, there was 52 of them turned on and 48 of them were usable. That meant that 4 of them were used for pilots. With 11N, we had 56, so we squeezed out a couple of these guard tones. The bandwidth is a little bit incrementally wider. We still have 4 tones associated with pilots, but that gave us those extra 4 tones. It's just the ratio. It's about 10% more raw bandwidth for the same modulation rate. Then we go to 40 megahertz channels. You see what we've done here is because we've got a contiguous 40 megahertz channel, we take the guard tones that are on both ends of that and put them back into useful, put them back to work. So here it's doubling, but instead of going to 112, I went to 114. Now, because the channel is wider, I need a few more pilots, so I have to give up a few, and I get to 108 usable, so I have 6 pilot tones in this case. And then this is the 80 megahertz definition. This is exactly the same idea. Again, we recover the pilots on each of the end of the pair of 40s, and that gives us 242 subcarriers, which you can see is well more than 4 times 56. So again, here we have 8 pilot tones distributed across the channel and guard tones on each end. Does that make sense to everybody? Because that's how OFDM works. That's what it means. Orthogonal frequency division. Each of these little tones is dividing the frequency up, and you're putting information on those tones.
So if you're sending the data, I'm sorry.
Yeah, that's fine.
If you're sending the data in parallel, how in the world does the
Well, this is where it gets really interesting, and it's probably beyond the scope of what we want to talk about today. But this is actually, in the radio, this is actually encoded in the frequency domain. Okay, so you have bins, and you put your bits in each one of those bins, and then you do an FFT to get to the time domain, and you send basically you send that FFT over the air. At the other end, basically you're doing a spectrum analyzer on the other end, and you extract the tones, and you're able to pick the bits out. You use the pilot tones to give you your phase and timing references, and you're able to extract the data coherently. That was kind of a bit of a deep dive, but I hope that didn't go over everybody's head. Okay, so now you've seen what we were talking about. So when we talk about these bits of information, so you can think you heard earlier today about having a 1 and a 0, right? Well, to generalize that, we create something called a symbol. So a symbol is a collection of multiple bits, and that's used to encode each one of those tones. And that's where the things like 32 and 64 and 256 Qualm come into this. I'm going to show you what that looks like in a minute. But the symbol's a really, really important concept, and it's a collection of 1 to 8 bits, and that's the stuff that's encoded. We don't send those 8 bits individually. We create a symbol, and we send the symbol over the air, and then we reconstruct the bits from the symbol. Because we are doing a modulation exercise with symbols. The tones and subcarriers, that was on the previous picture. Cyclic extension, this is a chunk of time when the radio is repeating what it's sent, and this is what gives Wi-Fi the multipath tolerance. So in this room, when I send the signal from here, there's a direct path, and there's also a path that bounces off the far wall. In order to deal with that multipath, Wi-Fi and all OFDM standards have cyclic extension. They repeat part of the symbol to make the system multipath tolerant. So that's actually wasted time. You have to account for that when you're doing your bandwidth calculation. Guard band, that's the space between the channels, as I showed you with the guard tones. Okay, pilots we talked about. And there's 2 types of channels. So we talked about the width of the channel. So most people think of a channel as, okay, well, it's this frequency and it's this wide. There's also a very important concept, and this is something you're going to run into if you do any research into looking at MIMO, or you're talking about multi-user MIMO or beamforming. It's the propagation channel. The propagation channel is not a single physical entity. The propagation channel is this room. It's the mathematical description of everything that happens between me as the AP and you as the client device. It's all the walls, all the ceilings, all the floors, and all the bodies in here. That is the radio channel, okay? And the radios, in order to do MIMO, you have to do a lot of very heavy lifting on the mathematics to actually figure out what's going on in the channel. And the fact that when people are moving, if doors are opening and closing, the channel is changing all the time. And forward error correction, these are extra bits. This is like a cyclic redundancy check. So the forward error correction are bits that are inserted to help the receiver make sense of what it's getting and to improve the reception of the bits. So it's redundant information. It cuts into how much useful information is sent over the air. But it determines whether or not you'd be able to accurately receive the message. Okay, so that's kind of the symbol list. I know it's a lot to take in, and I'm talking really fast. But those are some of the terminologies you run into if you start digging into this. Okay, so this is Qualm. Now, there's a couple other pictures missing here. I'm missing QPSK and I'm missing BPSK. What this is basically, so most people look at these pictures and they think, okay, the radio is sending all of these things all at the same time. What's happening is we talked about this concept of a symbol, right? So if I'm talking about a 16 Qualm signal, when I create my symbols, that's made up of 4 bits. So by the way, 16 is 2 to the 4, interestingly enough. Those 4 bits help you pick which location you're using on each transmission. So on this burst, I'm going to send these 4 bits to create this symbol. And what those 4 bits are encoded, literally, the first bit tells you top and bottom. The second bit says left and right. So, okay, so after the first 2 bits, maybe we're in this quadrant. Then the third bit's the same thing, left and right, 4th bit, top and bottom. So you finally, maybe the symbol will create that position on the constellation. So for the duration of one burst, we will be sending that amplitude and that phase. And this is what we use, for those of you who were in here before, we talked about IQ, so the in phase and the quadrature component. So the in phase is the amplitude this way, and the quadrature component is this way. So that's your IQ information. So if we now have 64 Qualm, that's 6 bits, and we do exactly the same process, left and right, top and bottom, and you just repeat, and that will pick the position on the constellation that you're sending for that individual burst. Now, if you look at a whole bunch of bursts over time, on any particular frequency tone, you'll eventually see this picture. But during any one particular burst, you're only going to be getting that position, and then that position, and then that position. Okay, so this is one of the things that's confusing, because I get numerous questions from people in the Wi-Fi business. Well, they go, okay, well, 64 Qualm, 256 must be 4 times better. It's not actually, right? That was 4 bits, this is 6 bits, and this is 8 bits. So for each burst, I'm only getting 2 more bits across here compared to here. So it's 33% better, which I'll take. But it's still not a 4 times improvement. So it's not magic beans. It's the way that you encode or modulate your transmitter so that your receiver can decode the symbol afterwards. Yep.
Are there any rules for going from blue to the next symbol?
No. No, on each burst, the symbols are created on a per tone basis. They're pushed through the transmitter. You do the FFT, and you send your result over the air. So there's no constraints on how the bits are transferred. Now, there's some fancy mathematical tricks in their transmitter to scramble the bits and to randomize them to make sure that you don't get too many 1s or too many 0s, because that can have some interesting effects sometimes on receivers. So you have an interleaver, so you take your bits that maybe have a bit stream like this. So you take the last bit and the first bit, and it kind of all gets jumbled through a scrambler. Then you interleave, and then you run it through your encoder as well to do the forward error correction. And so there's some rules that come in the mathematics there, but other than that, once the symbols are created, they're just pushed out over the air. Okay, so now we've got the terminology. Here's the basic physical elements. Each one of the tones that I showed you in the picture, that's a 312.5 kilohertz tone. And there's a whole bunch of them to create the 20 megahertz channel or the 80 megahertz channel. If you take that means the basic repetition frequency, you're sending a new burst every 3.2 microseconds. If you're not doing anything else, you're sending a new burst every 3.2 microseconds. Now the cyclic extension, this is the part I talked about to make the system multipath tolerant. So we talk about a long guard interval. So this is for large spaces like auditoriums or stadiums. You would typically not use the short guard interval there. That translates to about 800 feet. Light propagates at 1 foot per nanosecond. And this is the short guard interval. This is typically used in indoor and enterprise environments. And so these give you the multipath tolerance, and it is a physical parameter. Those translate directly to the physical channel. Okay, and then we talked about the modulation depth. That's a term that you'll hear. So BPSK is just top and bottom, so that's 1 bit. QPSK is 4 corners, that's 2 bits, and we get up to the 256 Qualm, which is the 8 bits. Now, if you take all those numbers and you just start multiplying them together, you start getting some interesting results. Okay, so here's the example. I've got the number of tones, which if I'm looking at an 802.11a symbol, for example, there's 52 tones. I've got 16 Qualm, so that's 4 bits per tone. And then this is my basic repetition frequency. And that gives me my raw on-the-air data rate. Okay? That's all I did. I just multiplied those numbers out. Very, very simple. So now you'll notice that for those of you who are familiar with the standard, there's actually 10, there's a list of 10 of them. There's MCS 0 through 9 for 11AC. We've only got 5 here right now because I haven't done anything else to the tones. I've only got the basic modulation rates. So I've got BPSK, QPSK, 16 Qualm. For a 20 megahertz channel, a 40 megahertz channel, and an 80 megahertz channel, I've just done that math, and these are the raw data rates. Now, this is for a single stream of data as well, because as you know with multi-in, multi-out, or MIMO, you can send up to 3 or 4 streams or even more, depending on which standard you're talking about. So this is on a per stream basis. I'm going to show you these numbers. Does everybody know what I'm talking about when I'm talking about streams, by the way? Okay, because you see you buy your Wi-Fi modem, it's 3x3:3. That colon is the number of streams that are sent at the same time. So MIMO, the power of MIMO was that it actually allows you to send multiple streams of independent data at exactly the same time. And it's because it's doing all this really cool math on the channel to actually work out how to extract those 3 streams at the receiver. Now, if I put the cyclic extension in, remember, this is wasted time. So for the long guard interval, which is the T/4, so that's 1/4 of the symbol is repeated. I go from here, which was 16 1/4, down to 13. And this is, I'm wasting less time here, so I've got 14.4 as my raw data rate. So now I've got two different sets here based on which cyclic extension I'm using. Okay, so that 585 has come down to 520 here. All right, now adding the next layer, this is the forward error correction. Again, this is redundant information put into the transmission so the receiver can go, okay, it can actually detect and correct bit errors. Okay, and depending on the coding depth, which is what they talk about here, or the forward error correction depth, it tells you how many bits you can correct. Okay. So when we do that encoding this is the most robust. This is if you're really far away and you're connecting at low signal strength. It's probably going to be connecting at BPSK. On BPSK, we use what's called 1/2 coding, which means for every 1 bit of useful information that I'm sending, I'm actually sending a total of 2 bits. So there's 100% redundancy in this system. All right. So that 13 that I had before has now become 6.5 because I'm only half of the bits that I'm sending are useful. Right? So again, we work out the same thing here. 5, 6 means for every 5 bits, I'm inserting 1 redundant bit for a total of 6. And so I get 86.7 up to 390. And down here, this is the short guard interval now. This is 433. On 1 stream, multiply that by 3, 1.3 gigabits per second. Okay? So that's exactly where those numbers come from. And it's not any more complicated than what I just showed you here. You just have to tease out all of these values out of the standard. Okay? So far, I haven't seen anybody, I haven't lost too many people yet, so I think we're doing good. All right. Is this interesting, guys? All right, cool. All right, now we're going to talk about antennas. First of all, we're going to talk about it at a very high level. How many of you know how to read an antenna pattern? How many of you think that there's distance information in an antenna pattern? Distance information. That's good. Nobody put their hand up, because there is no distance information in an antenna pattern. The only thing this tells you is how the power varies with angle. That's it. It doesn't matter whether you're 1 meter away or 100 kilometers away. This is power versus angle. So in a omni antenna is what this is typically referred to as. You have a fairly uniform pattern sort of around the antenna. This is to be the vertical pattern. This is probably a fairly long antenna. And we talk about the 3 dB beam width. That's where most of the energy is. You'll notice that the energy does not go to 0 outside of the 3 dB beam width. You can actually get useful coverage outside of that main beam, but it's obviously at less power. And so if you put these two things together, this is a simplified representation, but you kind of get something that kind of looks like a disc or a donut. All right, for a sector antenna, it's much the same thing. You'll see a few more terms thrown in. We talk about front to back. That's the power going forwards to the power going backwards. Now, sometimes you'll also see references to the front to side ratio as well, and that's just basically telling you what the power is going forwards versus the power going sideways. Now, we've done a little bit more math here. And this is actually what the three-dimensional pattern looks like. You can actually multiply these two things out because they're variable separable, and you'll actually get the sort of overall antenna pattern. So this lobe here corresponds to the main portion of the beam. All right. Now, this is one of the antennas that Aruba has on their price list. I'm going to use this as an example. That's the actual measured data. I don't like to work with measured data because it takes too long to code it. So this is actually a model that I created mathematically to represent that antenna. And why am I doing this? It's because to understand what's going on with distance, you need to do some trigonometry. Okay, so once the way you get distance into this is you have to define what the installation height is. So once you do that, then 20 meters out, I'm at 45 degrees. At 50 meters out, I'm there. At 100 meters or 200 meters, I'm in this portion of the beam. So you can actually see a great deal of your coverage is actually going to be in your main beam, because when you get in here, your angle changes really quickly. Right now, if we take those plots now and do this three-dimensionally, this is actually what it looks like when you project this onto a flat Earth model. So the side lobes that you're seeing in here, all these fine ripples, those manifest here as the ripples in the power pattern here. Okay? This is over a short range. This is 100 meters. And this is over a kilometer. So all of that is compressed down into the center of this picture. Okay, so all of this is just doing trig in the two-dimensional sense, and I'm actually plotting the antenna pattern. So now if I move up in terms of height, you can see that the rings are getting further apart, but the fundamental coverage doesn't change very much until you start getting very high. And now what you're doing is, because this antenna is quite narrow vertically, I'm actually starting to shoot the main beam over the edge of coverage. So this is an example of if you go too high with an antenna that has a skinny pattern, you're actually going to get degraded performance. Okay, so just that's why it's important to understand how that antenna pattern translates onto your actual coverage. Correct, because the antenna gain is going to be reciprocal, right? So if you lose pattern gain, it's going to affect your receiver as well as your transmitter. All right, now we're going to talk about beamforming. Right on time. All right, so I apologize for this. If anybody's epileptic, I hope that doesn't send them off in a... Okay, so this is the simplest model. You guys have probably seen this in your physics classes in high school. This is the idea of having a wave generator in the middle of a tank, or in this case, it's a wire with an electron moving up and down in it, and that's the most basic antenna beamforming, or basic antenna that you can generate is a simple dipole. The electron moves up and down, the waves propagate away from the middle. This is generally what an omnidirectional antenna is doing. Now, what's interesting is if I put two of those side by side, I actually get an antenna pattern that looks like this. I have a null going side by side, and that's because of this spacing. Okay, so beamforming is about spacing, phase, and amplitude. So the antenna spacing here is a half wavelength, and in this case, the waves just propagate away, and they reinforce in the up and down direction, and they cancel out side to side because these are in phase. Now, if I take that up to 4 elements, it's exactly the same thing, except now I've got these other things going on here. I've got these side lobes here, okay, and what that is that's just partial reinforcement in these other directions. Okay, so now all of these all have the same voltage on them, the same amplitude, and I'm getting a very directional antenna pattern now, because all I'm doing is manipulating the phase. So I'm forcing the energy, and the reason this is top and bottom is because these are omnis, so it's symmetrical up and down. But basically I'm creating more energy in this direction, and I'm getting cancellations out here. All right, now what happens if we start manipulating the amplitude? Okay, in this picture I had side lobes. In this picture, which is still 4 antenna elements, I've changed the way that the voltages are set up here. And so now I've been able to remove these side lobes. This is called the binomial array. And that eliminates the side lobes. And again, with the animation, okay, we've constrained that energy and we've canceled out the energy on the side. And if you adjust phase, okay, this is another simple example. If I excite this one first, then this one, then this one, then this one, I create a phase slope, and that will push the beam off to the side. Yep.
So you talked about explicit and implicit beamforming. Is this what you mean? One of them digitally and one of them not?
No. So let me come back to that. But that's an interesting question. Okay, so in this case here, I've just manipulated the phase. I've tipped the beam over, so now I'm shooting it to the side. Okay? Again, exactly the same thing, but this is done by virtue of phase. So now, it turns out the phase and amplitude, so all of these things make fairly pretty antenna patterns. Okay? You're going to see when we start talking about 11AC beamforming, pretty patterns is the last thing in the world that you actually want. All right, so 11AC, let's talk about this for a few moments. So first of all, this is an 11AC protocol. It works with clients that support 11AC. It does not support 11N. It does not support 11BG. It's an 11AC solution because of the explicit beamform that we talked about. There's a sounding protocol. The packet gets sent over the air. The client says, okay, I hear antenna 1, antenna 2, and antenna 3 on the AP like this. It takes that information, compresses it, and sends it back to the access point. And then at that moment, the access point and the client have a perfect mathematical representation of the channel, okay, based on the estimation that's been done. It knows exactly where every single reflector is in the room, where all the walls are, because of that mathematical representation of the calculation that's done of the channel. So that's where we talk about a channel estimate. It's actually taking a mathematical snapshot of this room, of your cubicle, of wherever you are, okay? 11AC beamforming is standards-based. So you can say whatever you like about standards. One of the things that's true about it, though, is this is really the collection of thousands of smart people getting together and deciding that this is the right way to do this. Okay? And again, if the standards process is done badly, you get 11N and beamforming doesn't go into the product. It's done in baseband. This is really, really powerful. That means that basically it's very forgiving. You can make beamforming work better by selecting the right antennas, but it will always optimize the system based on the antennas attached to it. So if you screw up, it's still going to try to get a benefit out of the system out of it. Okay, so it's really quite powerful because it's completely generalized. And it actively tracks the user, so it has a burst by burst. It updates the position 40 times a second. There's a sounding packet sent to each user every 25 milliseconds. So this is the sounding process. This is explicit beamforming. This is the only thing that's standardized in 11AC. Okay, a sounding frame is sent. These are special frames. It goes out over the air. The client responds, and then the beamforming access point sends back a beamform burst of energy with multiple streams on it. One of the things that's different, and so beamforming is actually not a great name, because what it's actually doing, so if you think about some of the analog beamforming solutions you see, this is basically where they're either physically turning an antenna or changing some pin diode switches so they're shooting energy out in different directions. That actually is only doing one thing. It's trying to maximize the signal strength at the client. The problem is that works great if all you're dealing with is a single stream. There's a couple things going on in the industry right now that are really, really cool. One of them is the Samsung S5, and apparently the new Apple phone, once it comes out with 11AC on it, these devices will support 2 streams on them. So conceivably, that means that you're talking about data rates to a handset upwards of 600 megabits per second of useful TCP throughput. But in order to do that, the beamforming not only has to maximize the signal strength, it also has to maximize the channel to provide multiple streams of data. Okay, so how does that manifest? Because everybody's got this picture in their head. Is, we're in the business of doing this, making these sort of pretty patterns, steering a beam over here, and life is good. That's not actually what happens. Okay, so first of all, I'm going to back up here just on one slide. This is what, when you go reading these papers on 11AC beamforming, They tend to start here and they go down from there. Okay, it's pretty scary. So what does that mean? What is that physically? It turns out these are the 3 antennas on the access point, and these are the 3 antennas on the client. This could be a laptop, could be anything. Okay, they're shown here as being regularly spaced. They could be spread out, whatever. Okay, so what this is actually doing, each one of those things basically corresponds to a point on the graph. So if we look at antenna 1, that's the red line here. Okay, and so I've got at the client antenna number 1, I've got this received here. Antenna 1 on a client 2 is here, and antenna 1 on a client antenna 3 is here. Sorry, big mouthful there, sorry. But basically what it's saying is this is what I measure. From the first antenna on the AP, my 3 antennas on the client measure those 3 points in space. Same thing for the second antenna, and same thing for the third antenna. That is actually what beamforming is. That's what the sounding process is doing. It's measuring the channel. It's building a channel estimate, which, by the way, is what this is. Okay, and then it's doing the math on that and sending back to the AP. So this has some really interesting implications. Okay, so now this is line of sight. This is outdoors. There's no reflections around. It's just wide open space. So that it's going to turn out kind of the way you think. There's your AP. There's your client. Okay, does the beamforming process. You get this lovely antenna pattern. You can see it's tipped over here just a little bit to the right. This doesn't show it well, but it is. You'll have to take my word for it. It is tipped over here a little bit, and so it's maximized the signal at the client. In the absence of reflections, that's all you can do. Now, what happens if I put 2 walls in here? Same AP and client, same distance apart, but what is the optimum antenna solution in this case? That. Okay? Now, that doesn't look anything like the picture I just showed you. And the reason is because now the AP and client know that the walls are there. So it's going to say, okay, well, I'm going to shoot some energy over here, which is what you're seeing here. And I'm going to shoot some energy over here, which is why this is tipped over more. And that's going to improve the signal strength of the client. That is the optimum antenna pattern. It isn't anything that's pretty. It's not beautiful. This is the optimum antenna excitation for the channel that the system exists in. Now, what happens if you do this with multi-stream clients? Something really interesting happens. Remember that we have to help the system separate the three branches of information so the receiver can receive it cleanly. So stream 1, stream 2, and stream 3, the antenna patterns are all different. Okay, you can't do this with an analog solution because they only transmit in one direction. But with a digital solution, I can actually beamform in baseband, and I have 3 different amplitudes and phases for the 3 different streams. So I get 3 different antenna patterns for the 3 streams of data that I'm sending. Really, really powerful stuff. And it even gets more interesting. I'm going to show you that in a second. But this is how this manifests. So now what I've done here is I've just isolated stream 3. This is after the beamforming. I'm sending the same information over all 3 antennas, and I'm weighting it on amplitude and phase. So these are the 3 signals that show up. That doesn't look like much, but remember this is vector math. So what happens when I add them all together? You get this. Stream 3 shows up at the client's antenna 3, and these 2 are nulled out. This is a really, really important result. Most of you should have heard about multi-user MIMO by now, because it's been talked about for wave 2 of 11AC. This is multi-user MIMO. Multi-user MIMO is a general case of a single client with multiple antennas. Because instead of being attached to the same client, these are attached to different clients. Okay? So if I'm sending stream 3 to this guy, I don't want his information going here because that'll be an interference source. So it sends zeros to those 2. And if you extend this now, it does exactly the same thing. Stream 2 shows up on the middle antenna, and stream 1 shows up on the leftmost antenna. So what it's actually doing, it's beamforming in a sense, is taking the channel, and it's like pulling blue wire, pulling RF cable across the room, and basically connecting antenna 1 to antenna 1, antenna 2 to antenna 2, and antenna 3 to antenna 3. That means you actually have a situation where the receiver doesn't really have to do any work to actually extract the information. And that's how multi-user MIMO works as well, because it doesn't have the benefit of having multiple antennas when you're talking to 3 different smartphones. So the AP has to do all the work in order to isolate the channels. So this is really cool.
So how do you separate the optimize over
Great question. I love having a straight man in the audience. This is what happens. It actually does this calculation. If you go right out to the extreme, it actually does this calculation for every single tone. Okay? Now the reality is that tone 1 to tone 2, it's not going to change very much. So you can group these in 8s or 16s instead of 1 by 1. But that still means that you're generating, remember, I have 242 tones. If I take this to an extreme with 3 streams, I'm beamforming 726 different antenna patterns when I do my burst. Now, in reality, it's probably every 8, so it's down to about 100 different antenna patterns on every burst. But you can't do that with a physical antenna. This can only be done with baseband processing. This is why this is so incredibly powerful. And if anybody tries to tell you it's the same thing as just steering an antenna, they couldn't be more wrong. This is a mind-blowing, totally differentiating technology. There's a question at the back? Yeah, so most of the, well, so in wave 2, it's only on the downstream because the AP is the device that has all the processing power and is the aggregator of all the information. You could presumably do this, but why would you have a client talking to multiple APs in the case of Wi-Fi, right? So it's right today, and there's no talk about extending this. Today, this is in the downstream direction. But if you think about even today, the asymmetry is not quite as strong as it used to be, but it's still fairly asymmetric, and so there's a real benefit for systems operation.
So the access point does the estimation, essentially sends its answer to the client and says, hey,
Actually, the totally opposite. The client receives the sounding packet. It does the estimation, sends back to the AP, and then the AP does all this math. Right? So this is really cool stuff. But it also means that traditional solutions where they were thinking about steering an antenna, that's the wrong way to do it. And 11AC with beamforming is an incredibly powerful technology. All right, so I'm down to my last couple of slides, and I'm right on the stated time that I was supposed to get. So, all right, now, so this is one of the outdoor products that I produce with Aruba. So I really like this number. This is pretty cool. 850 megabits per second. That's 3 streams of data running to a MacBook Pro. That's pretty neat. But the thing that I actually get more interested in is over here. This is 600 meters, okay, 3/8 of a mile. Beamforming is turned on. I'm getting 185 megabits per second at 600 meters. That's incredible. I've been in this business for a long time. That's pretty freaking awesome. And this is to an unmodified MacBook Pro, just using the antennas that are in the cover. Okay, so that's interesting. What about a smartphone? This is a Samsung S4, which is a single-stream 11AC client device. All right, I'm not working at 600 meters, but hey, 75 megabits per second at 300 meters, not too bad, right? So, because a handset basically runs out of juice in the uplink direction, it doesn't have enough transmit power. So pretty powerful stuff, and this is actually now isolating the effective beamforming. You can't compare the last 2 charts because these were done on different times and different places. But this is beamforming on. This is beamforming off. Okay, so pretty powerful stuff. And that is the end of my slides. There was a question? So the indoor environment, it's exactly the same thing. We see connections inside at the very highest data rate out to, depending on the space, between 125 and 200 feet. Okay? So if you're dealing with interference and other things, like there's lots of reasons why that's an optimistic number. Because when you do a real deployment, you have lots of APs. But if you isolate it and you do that same test indoors, yeah, we get the 1.3 gigabits per second or 900 megabits per second useful out to about 150 feet in an open space.
So your wavelength is on the order of like 5-6 centimeters.
Correct.
So I mean, a consumer device is pretty small. Like, how do you get the baseline to get diversity?
So the critical spacing turns out is about 1/4 of a wavelength. And the other thing that you see in laptops and consumer devices is they actually use multiple polarizations. So outdoors, we put multiple polarized antennas on the solution. Indoors, the environment takes care of the polarization because when you bounce off of a wall, it spins the polarization. Any other questions, guys? Okay. I'm around for the next couple of hours. You guys have any other questions? Thanks a lot.